Hi, guys. I tried to post this video yesterday, but I was too punch drunk from not getting enough sleep, so I didn't have a coherent, excuse the pun, a good explanation of some of the things I was trying to say about the various gas lasers on this table. So we're not going to run the actual experiment right this second in this video, but I wanted you to see the Cavendish apparatus because I'm going to post a video of some actual runs from it eventually, and I'm also going to upload a link to some articles that walk through the Cavendish analysis, and it's the kind of thing I'd like you guys to be able to do. This actual instrument that we've got on the table, tip the there we go, tip the camera so you can see it. It's this, there we go, this thing right here, this white metal frame that encloses the actual torsion pendulum. This piece of equipment was purchased by EKU in the early 2000s sometime, but Dr. Choka had very little success trying to run this experiment over in the old science building, and his assumption was that vibrations coupled through the floor were just killing the performance of the instrument. So we're sitting on top of these 18-inch thick optical tables here. Each one of them weighs about as much as a Toyota Corolla. There are two of them bonded together at a mating plate that's, gosh, what, 2 times 3/4 inches thick steel. So it's essentially one rigid body that weighs as much as 2 commuter cars, built out of flat steel sheets with a honeycomb steel structure in between. So it's a very rigid object. It weighs a ton, so in order to get it to vibrate a lot, you have to put a huge amount of acoustic power in it, and me stamping up and down on this floor is probably not sufficient to do that. And then we can further isolate it from the environment by floating it on air cylinders. So the legs, you can see, get my finger on the right part. There it goes. You can see there's a leg right there. That leg actually contains a pneumatic piston that can be used to raise the table up off of the grade. We're on a concrete pad here. The concrete floor is not the roof of some other level. It's the actual foundation of this level of the building. So we should be pretty inoculated against vibration coupling in from the environment. You might be skeptical that that's an issue. You might say, how can a small amount of acoustic noise perturb an instrument like this? But it's precisely because we're measuring something very sensitive that a small amount of acoustic power coupled in as noise can have that effect. The data that shows up in my PhD thesis was all collected. It's like Christmas morning at about 3 a.m., just because that's when I was getting the best results, because the building was absolutely abandoned by all decent human people. And the elevators had stopped running and everything was shut down. So there was less vibration in the area. And I could get data other than that, but I just got better results when everything was quiescent. All right, so we are going to be working with these massive optical tables. I should, for the sake of honesty, note that they're not actually riding on the air pistons right now. I don't think we need that level of isolation from the environment. But at the moment, the table is resting on a hard stop. And the reason for that is I have to buy more 25-cent polyurethane tubing to float the tables. I did all the plumbing to run dry nitrogen or compressed building air, set up for both, into the table to float it. But I need like another 8 feet of tubing, so I got to go spend $2 on that. All right, so we've moved to an environment where acoustic perturbation should not be a big factor, and hopefully that will allow us to run a decent measurement with the Cavendish apparatus. So we'll talk about that a little bit, but the first thing we have to talk about is the laser. So you can see there are 2 lasers on the table right now for this experiment. Let me point them out. I have no idea where to put this microphone. Hang on a second. So the two lasers that are the things I want to talk about right now are both gas lasers, which means they're these little black cylinders, maybe 14, 15 inches long, 8 inches long, 18 inches long, excuse me. And they have a reservoir filled with gas in them. That gas is excited. We'll talk about that process a little bit more. And it ends up giving you a laser emission. So the first one we're going to use is this red HeNe. Let me see if I can get my finger on it. There we go. And it has a couple of bags of copper-colored little spheres on it right now. Let's actually scoot in closer. We'll take a look at that. Okay, you can see there's this tube, a black tube that's resting in those two V-clamps, and it has what appears to be a few hundred or 1,000 little copper balls sitting on top of it. Those copper balls are copper-coated shot. I can't remember if it's actually lead shot or steel. They're just there to add a little bit of weight to it. So that's kind of a dinky mount for a laser. It's not substantial, it's not robust, and it won't do a very good job of managing vibration. But for the same reason that these tables weigh as much as a car or two, the vibration magnitude can be managed a little bit just by weighting up the laser. So there's some heavy stuff sitting on top of it to help damp out vibration. Heavy is good in this case, right? Okay, so the laser, let's wander in again. When we're over here, you can probably hear Kate Bush playing in the background, so that's wonderful for you. All right, the laser is being emitted at this end of the tube, hitting a mirror, hitting another mirror. Over here, it's going through some stuff that's mysterious at the moment, and then it's going off towards the apparatus. But what I want to talk about right now is the color of the laser. It's red, like 99% of the lasers you see. And, oh, I can't do two things at once, it turns out. If you look at this spot, it looks pretty big. It's not actually that big. It's blown out. So we are looking at it using a CCD through a pinhole camera, which is a terrible way to do any of this. That's why everything looks terrible. That's why I look terrible, is because of the pinhole camera. It's not because of my personal failings. The pinhole camera has a CCD behind it. The CCD is divided up into physical pixels, and each pixel is detecting some amount of light. But with intense light, you get this blooming effect where one little bin in the charge coupled device will have charges that accumulate when photons hit the CCD. It'll have charges spill out into the adjacent bins, into the adjacent pixels. And that's why you're getting this blooming effect, because this intense coherent light is hitting the CCD and overwhelming one pixel and spilling off into the adjacent ones. So the spot looks bigger than it actually is. And if you're in here staring at it with your eye, we should talk about, first of all, how to do that safely, and when not a laser poses an eye safety risk. If you were just looking at it by eye, you'd say, oh, it's about 1.5 millimeters in diameter. And that's actually not something we can say easily, because the function that if we had an x-axis for dimension, position, and a y-axis that was the intensity of the light, the beam doesn't go in a square, right? It doesn't do some nice little flat thing. So how wide is this thing? Well, if it was just a step function, I could tell you how wide it is. I would measure the width of that. But instead, it's this Gaussian. So we talk about the full width half maximum as a way to measure the size of the spot. All right, so that's just me being fussy, right? Kinda. The other thing to keep in mind is that just like the CCD, your eye is not an ideal perfect mechanism for measuring light intensity. It's not necessarily a linear device. So when I look at a spot and I go, oh, it's that big, do I know that my eye is responding linearly to the low intensity light down here the same way it is to the high intensity light up there? I don't. So it's actually really hard to estimate the size of a spot by eye. You'll get it wrong. We can measure it. We don't need to for what we're doing, and so we won't. All right, laser. It's red. This is a very long-winded video for me to say, look at this laser, it emits a red light. We're going to talk about that a little bit more in the next chunk of video. I'm going to pause this for a second and run and get something, because I just thought of another thing we should play with. All right, I'll be right back.